Thank you for joining me for the recorded tutorial for the session 2 or day 2 of Boulder 2022. In this recording, I'm going to go through in quite a bit of detail an ACE model using twins only with a continuous variable. So opening up that script, and then I'm going to start by setting my working directory. And it's already clear my environment. I'm going to load my libraries, so loading OpenMx, and then the PowerFun source here. That is a script of functions that Brad Verhilst has written in order to do the power calculations that are used at the end of the script. He also has a recording on doing power calculations if you'd like to look at that in more detail. It's in the recorded lectures for day 2. Loading up the data. This is a smaller data set than what we used on the day of the tutorial, just so that we can start to see some differences in power when we later add in some siblings. So now I'm going to start by loading some objects. These objects here are just ways that we can simplify, or if we make a change, it can then populate readily throughout the rest of our script. So we've got a number of traits. This is useful if later we wanted to change a script into being a multivariate trait. I suggest you only do that when you really are comfortable and know what you're changing in a script and how that's affecting the other objects in the script. This is the number of individuals. So this is what we would change when we include siblings or other people in the family. This is the total number of variables, so number of traits by the number of individuals. That's going to give us like the dimensions of our variance covariance matrix. So looking at how all of these cross-trait, cross-twin variables covary with each other. But for us at this point in time, it's pretty simple. It's going to be a 2x2 matrix because we have only one trait and we have only 2 individuals. So we can actually see that if we highlight that and copy that below. So this is another useful trick, is that if you are highlighting an object or something within an OpenMx script, then you can start to see these little boxes and you can see where else they are appearing in the script, and you start to be able to troubleshoot if something's going wrong. It's very useful. And if you also are highlighting an object and then I'm using Control Return, I'm using a Mac, then it populates down here in the console and you can see what is in that object. So we've also loaded here our traits of interest and our covariates of interest, one for each of our individuals, each of our twins. Now I'm going to separate my data into an MZ data and a DZ data object, giving it the relevant columns of data in my object, which is based on these that we just created. And now let's have a look at the descriptives. And we can see here that the means of the twins are about 0. The average age is 20. This is the same for MZs and DZs pretty much. And we've got about half and half males and females. Males are coded 1 and females are coded 0 in these data. Here is our variance covariance matrix across both our traits and our covariates. And we can see here that our MZ twins are covarying at 0.73 and our DZs are at 0.44. So our DZs are more than half of what our MZs are, and that leads us to think, okay, well, we'll start with running an ACE model. And on day 4 and in those lectures and tutorials, then Matt will talk more about the biases that come with like being restricted to only being able to run an ACE or an ADE with just these data. We can also have a look at, for example, maybe we want to have a look at the what am I trying to say? Let's have a look at a plot, a scatter plot. We can sort of see if there's any potential crazy outliers. I've done something wrong there. There we go. There's our MZs. And there's our DZs. So if I have a look over here and we flick between them, we can see that correlation pattern is stronger for our DZs than our MZs. So this here is our MZs and this here is our DZs. And we're going to load some objects. So these again can populate throughout the script. Oops, sorry, here we go. Okay, now we're really starting to build our model. So here we're creating some matrices that are going to be used in setting up our expected means for our model. And we're going to, this is where we're going to incorporate our age and sex effects. So this is in a situation where we're looking at the contribution of genetic variance and the shared environment and the unique environment to a trait, but we know that there's some age and sex effects, and we don't want to be looking at those because for a start, our twins are all going to be the same age if they're measured at the same time. And so that's going to mean that we might be artificially inflating our C if age has a very specific effect, and we've got our MZs and our DZs all being the same age, all being measured at the same point in time, and it's going to potentially introduce a bias to our estimates. Same with sex. I mean, our MZ twins are always the same sex, our DZ twins are not necessarily the same sex, and so if there's a substantial sex effect, then it's going to mean that our same-sex twins are going to be more similar to each other than our opposite-sex twins, and it could just be a matter of sex. It's not necessarily something that is to do with the shared environment or to do with the genetic similarity of individuals. So these are some of the main covariates that we're thinking of when we're looking at twin models, especially if we happen to measure our twins at the same point in time and we know that they're the same age at the same point in time. Okay, so we're doing this by creating a matrix that is going to estimate the effective sex. So this intercept is essentially kind of like the intercept of a regression, and then we're going to have the effective sex and the effective age as being like beta weights. So this is a single row. And then we've got the number of columns is going to match up to our variance covariance matrix. So it's going to be the number of traits that we've got. So we've only got one, and that by the number of individuals, and we've got two. So it's going to be 2 columns wide, and it's going to exactly map onto our variance covariance matrix. And we can have a look at the size of this matrix just by highlighting that object name, and then we get some information on what this object is. Again, that can be very, very useful if you're needing to troubleshoot some scripts that you might be playing with or tweaking, which again, I only recommend you do after you're comfortable with manipulating the scripts. So our beta, however, it is going to be just the number of variables. So we need a beta for each of the variables that we might have in a script. In this case, we have one variable, one trait of interest, and so it's just a 1-by-1 matrix. And here is the estimated start value, and this is the label that we've given it, beta S or beta sex, and this is the name of the matrix. So the matrix name is what's going to be used in any subsequent algebras, MX algebras, not the name of the object. The name of the object and the name of the matrix often serve a different purpose, so it's good to be able to disentangle those two. So here again, same thing for our beta age. And then we start off, this is our first definition variable. So the definition variables in OpenMx are actually pulling in data. So it's saying, okay, well, I'm going to go and pull in the data for this particular family and this particular individual in this family. So, or this particular row and this particular column, which in our data set happens to be family and individual. So a definition variable is specified really by having this word data dot in the label, and then what comes after the dot is the variable name in your data set. So our data set had sex 1, sex 2, age 1, age 2 as the names of the covariates that we were interested in. And so this is literally saying where in our data set to go and get some information and pull that in line by line, family by family into our model. It's not free. It's actually data that is already got a value. So we're not estimating this. It's going to inform the relationships among our data points in our model so that we can estimate our betas for age and sex. And here is where we're describing the nature of that relationship. So we have our expected mean is going to be the intercept plus the estimated effect of sex using our actual sex information, our data, and then the estimated effective age using an actual measured age information in the data set. So we have this here, which is describing the effect of our means, and it's these matrices either multiplied together and then summed. And if we want to have a look at that, we're not going to be able to see that at this point in time because it hasn't yet been calculated. But this is when we might be able to use MX-eval after we've put the final model together to see what's going on in that actual object, or what's being described there as a starting point, like before the model's actually being estimated. So then we go through and we start loading up our objects that are matrices that are holding the estimates that are going to be, or the parameters that are going to be estimated for our additive genetic variance, our shared environmental variance, and our unique environmental variances. And again, these are the size that is based on the number of variables that we have in our data set. In this case, it's just one by one. We have one variable. And then we set up an object that's going to be the total amount of variation. So that's just the sum of our A, C, and E components. And then we have our covariance for our MZ pairs and our covariance for our DZ pairs. At this point, we're just specifying that our DZs are half of what the total additive genetic variance is, which is going to be what our MZ pairs have. And that's because DZs on average share half the genetic variation. In later scripts, we will go through and we'll specify this in an alternate way, gradually leading up to pulling in measured genetic relationships between DZ pairs. So here's where we finally specify our expected variance covariance metrics for our MZs and our DZs. And we can see that we have our variance on the diagonal and our covariance on the off diagonal. It is a 2 by 2 matrix. They're the same size. They have to be the same size. And it needs to be the same width as our means, because we're going to have our means needing to be a matching dimension in terms of the matrix size. So now we actually then specify our data in a way that OpenMx is going to be able to read it. It's saying that it's a raw data, so we're actually giving it observed data. This is how we separated our data up here. So this is just separating it for R, and now we're using that and we're applying this MX data function to it so that it is recognizable in the OpenMx optimization process. Now we're creating expectation objects. So this is then putting all of our expected variance, covariance, means together for like describing the actual model. This is our expected model of relationship in our data. And this is specifying what kind of optimization we're going to do. So we're going to do maximum likelihood optimization to obtain the best estimates, the best parameter estimates that will describe the relationship in our observed data, minimizing the fit between our model and our observed data. And then we've got our objects that are going to be used, like just little lists of objects that are then going to be put into our models. This is sometimes useful if we've got a lot going on in a model. It's also useful to separate out the definition variables from the rest of the objects, only because definition variables must go into a model that has a data object. Otherwise, you're going to get errors thrown at you. And sometimes we want to use these other objects in final models where we actually don't have a data object. And this can just be a simple way of keeping those two things apart because of the way that OpenMx handles things in the background and reduces the chance that you're going to get errors in your data when you try to run the model. So now I'm just going to put them all together. So this is where we take all the pieces that we have created, all those objects, and we stick them together into a submodel, because in order to estimate we're going to need all of those pieces of information. Some of them are specific for the MZ pairs, some of them are specific for the DZ pairs, and some of them are common across both. This multi-object at the very end is saying, okay, well, now we actually want to get the model fit that is across all of our data. That includes our MZs and our DZs, even though we had incorporated those and built those as two separate groups. We actually want to be fitting our model across all of our data, not just across one of those groups. These objects here are just a way that we can kind of pull data together and have a look at it after we've run the model, and we can also run confidence intervals on objects. It's quite a flexible function, this one here. So we're going to be asking for confidence intervals on columns 4, 5, and 6. So that will be 4, 5, and 6, and that is going to be the standardized variance components of A, C, and E. Now we put our model together. So we've got our MZs, our DZs. This is asking for it to be fit across everything. And then we've got these extra confidence intervals and an object that helps us pull out information. Now let's run it. We're running it with confidence intervals true. It's a fairly simple model, so it should run pretty quickly. If you're running a complicated model, I would recommend running it, first of all, with confidence intervals false. This is getting a summary object. And now that we have our output, let's have a look at our output. So here we have the estimated parameters. These are unstandardized. These are just the raw estimates that came out of our matrices. We've got the name of the, these are our labels, and this is the matrix that it came from. This is the size. And here are our estimates. So we have our intercept, -3.4, which is substantially different from the approximate value of 0 that we started with. But the reason for that is that we have a positive effect of age, and our average age is 20. So if we do an average age of 20 by the beta of age, then we get a value of 3.4. So that will bring our intercept or the value, the expected mean, back to 0 on average based on our age adjustment. And then we also have our sex effect. So our males are scoring slightly higher on our trait. So for every male, they're scoring 0.25 units higher on our trait. And that makes sense also in that our sample is about half male, half female. And our mean was originally, I think it was about 0.15 or something like this. So about half of that beta effect in terms of above 0. And that's consistent with what was simulated, which was to have a mean of 0 and to have an age effect and a sex effect. So here we have our unstandardized variance components that is just being estimated, and the standard errors. And then we can see here that they're very similar to the standardized variance components, which makes sense because our variance was pretty close to 1. And we have our confidence intervals being requested, and we can see that C is actually crossing 0. So a little bit, maybe technically not significant with a 0.05 cutoff. Okay, so here we have our parameters. We've got 6 parameters that were being estimated, 1 for each of the variance components, 1 for each of the covariates and the intercept. We have our degrees of freedom, which is a total sample size, or our sample size less the parameters being estimated. And then we have our log likelihood, our negative log likelihood. So we've got the information here that we might need if we are going to look at the model fit, a significant loss of fit for any kind of nested models. So what else is here that we might, these might be fit statistics that are of interest to you. And we've got the optimizer, which was just the default optimizer. We can see that I've actually got an older version of R running on my desktop, and we can see how long it took to run. So now let's have a quick look at the power, as well as here's some ways of pulling out information. So this is part of the defaults, just being able to pull out that kind of output. The var_c is calling this particular object that we created at the very end of our script, and is saying, okay, well, let's go and actually pull that information out in a nice, neat format. So here is where we start to set up our power calculation. We're going to start by taking our full model, and we're going to drop A. We're going to fix that to be false, and that's going to give us a fit index, or a change in log likelihood, for if we don't include A in our model. We do the same for C if we don't include C in our model. And then here we can actually see, so the difference in log likelihood if we drop A is a difference of 29. The difference if we drop C is a difference of 3.8. And then we're going to get our sample size. So we're not interested in p-value at this point in time. We're really interested in the model fit. And then we're going to use that information to create a weighted non-centrality parameter. You can have a look at that by highlighting that object that we've just created. But the whole purpose of doing that is that these are the pieces of information that we are going to plug into the power function that is in the script that was written by Brad. And then we're going to be able to get our power calculation for A and for C just by running those 2 lines of code. So here we have almost power 1.999 for A, and here is our power for C, which is 0.62. So stronger power for A than for C, but both were reasonable, and we will see how they change when we add siblings and change the parameterization of the script. So I hope that ran smoothly for you all, and I will stop this recording here and then create a separate one that is for all the additional ways that we're going to run these scripts. Thank you.